Hi, I'm Nicholas Dwork, and in this lecture we're going to discuss functions of real numbers. That is, in this lecture we will discuss functions that map the real numbers to the real numbers. A function f is continuous at x naught means that the limit as x approaches x naught of f of x exists. As an example, here are two axes and here's the location x naught. Here is one such function, and this function approaches the same value from the left and the right at x naught. Therefore, the limit as x approaches x naught of f of x exists. Since the function approaches the same value from both sides at x naught, it is continuous at x naught. In fact, this function is continuous everywhere. Here's a different function. Here the function jumps at x naught. Since the function approaches two different values from the left and the right, the function is discontinuous at x naught. It is not continuous at x naught. Here's another example. F of x is equal to the sine of 1 over x. Now, here's its graph. It's sine, so it oscillates, but the oscillations increase frequency as you get closer and closer to x equals 0. One can get arbitrarily close to x equals 0 and find function values that range between -1 and 1. Therefore, this function is not continuous at x equals 0. A function f is continuous means it is continuous everywhere in its domain. A value x is a root of f means that f of x equals 0. The R-level set of f is the preimage of R under f. And the 0-level set of f is the set of all values that map to 0. That is, it is the set of all roots of f. In applications of computation, we often want to find the root of a function. Example applications. In computer graphics, intersecting a light ray with a surface often comes down to finding the root of a function. You might want to find the sustenance required to maintain the population of a particular species. Or you might want to find the time of collision of two moving objects. Since we often want to find the root of a function, now let's discuss a method to achieve that. We're first going to assume that the function is strictly monotonic. What does that mean? A function is strictly monotonic over its domain means that it is either increasing or decreasing over that domain. A function f is decreasing means that f of x is greater than f of y for all x and y in the domain where x is less than y. And a function f is increasing means that f of x is less than f of y for all x and y in the domain where x is less than y. If a function is either increasing or decreasing, then it is strictly monotonic. Here are two examples. The function on the left is increasing. It goes up as you move to the right. The function on the right is decreasing. It goes down as you move to the right. And both of these are strictly monotonic. Okay, so we're going to assume that the function is strictly monotonic, and we're going to restrict our attention to an interval ab, and we're going to assume that the function that maps the interval ab to the real numbers is strictly monotonic in either f of a is less than 0 and f of b is greater than 0, or f of a is greater than 0 and f of b is less than 0. Then we can find a root with the bisection method. So what this means is we know there's a root within our interval, therefore it's got to be negative on the left and positive on the right, or vice versa. If that's the case, then we can find a root with the bisection method. How does the bisection method work? We start with our interval ab. We evaluate our function at the endpoints of this interval, so now we've got f of a and f of b, and then we divide this interval in half. We then evaluate the function at this middle point. We see in this case it's positive. Therefore we know, since this function must be monotonic, it's going to be strictly decreasing in this case, we can exclude this half of our region. We know the root is not here. We divide the remainder of the interval in half, we evaluate the function again, and this tells us again that we could exclude this portion. We divide the remainder in half, we evaluate the function, we see this time it's negative. Again, since we know the function is strictly monotonic, it's decreasing in this case, therefore the root cannot be to the right of our new evaluated point. And we know that the root is within the remainder of this interval here. We divide in half, we evaluate, we eliminate. And you can see this was the function that I was trying to find the root of. We indeed have limited the region where the root lies. Here's how it looks in code. We accept inputs a and b, where a is less than b, that's our interval of interest, and epsilon greater than 0, that's going to be the error that we're willing to tolerate. We set our min equal to a and our max equal to b. We evaluate the function at our min, and then we calculate the midpoint between the min and max points. While our max minus our min is greater than or equal to 2 epsilon, we're going to conduct the bisection iterations. Now, why do we have 2 epsilon here? Suppose this is our interval of interest, and the gray regions represent portions of the interval that we've already eliminated with the bisection method. Suppose further that the remaining portion, where the root might lie, is less than or equal to the 2 epsilon in length. We're going to return the middle point. And so therefore we know we cannot be off by more than epsilon. We evaluate the function at the new middle point. If f of our min times f of our mid is less than 0, that means there are different signs. Either f of our min is positive and f of our mid is negative, or vice versa. And that means the root lies to the left of our mid. In that case, we can eliminate the right half. We do that by bringing our max down to our mid. If f of our min times f of our mid is not less than 0, that means we could eliminate the left half, and we do that by setting our min equal to our mid, and correspondingly f of our min equal to f of our mid. We then calculate the new middle point for the new our min and our max. This concludes the iterations, and we return our mid. There are alternative stopping criteria to the one listed here. Perhaps we're not interested in the x interval. Perhaps we want the function close enough to 0 before we exit. So an alternative stopping condition is while the magnitude of f of our mid is greater than epsilon. Note that this stopping condition is only appropriate for functions that are continuous. Otherwise, there may not be such a point in our function. In addition to whatever stopping criteria you choose, it is common to limit the number of iterations to a maximum. This ensures that you're not stuck in an incredibly long loop. How do you do that? Well, first you add an additional input, max iteration, which must be greater than 0. You add a condition into your while loop, so in addition to your stopping criteria, you say while our max minus our min is greater than 2 epsilon and iteration is less than max iteration, and then you got to keep track of the iterations. So you set iteration equal to 0 before the while loop, and then you increment it by 1 within the while loop. We've already discussed applications of finding the root. Many more applications of computation come down to finding the input that yields the best output. And this frequently amounts to finding the input that yields the maximum or minimum value of a function. Examples of this: find the drug dosage that minimizes the time to recovery, find the amount of resource to purchase and process in order to maximize a profit, or find the radiation beam intensity that maximizes C minus T, where C is the amount of cancer killed and T is the amount of other tissue saved. One way to find the best output is to use golden section search. This is applicable when you know the minimum or maximum that you seek is in an interval, and there is only one minimum or maximum in that interval. Furthermore, and for the remainder of this discussion, I'll assume we're seeking a minimum. I hope you can adapt as needed if you're seeking a maximum. The function must be decreasing to the left of the minimum and increasing to the right of the minimum. Before we discuss golden section search, let's discuss a slightly easier approach. We will start first by considering searching in thirds. How does this work? This is our interval a and b, and we're going to divide up this region into thirds. Then we're going to evaluate our function at these new candidate points. Okay, in this case, we see that the function is positive on the right point and negative on the left point. Since we know that the function is strictly increasing to the right of the minimum, it must be the case that the minimum lies in the left-hand 2/3. That is, we could eliminate this right-hand third of our interval. What do you do then? You divide up your remaining section into thirds. You evaluate the function. You see that the point on the left is less than the point on the right. Again, the minimum point cannot lie to the rightmost third. We again divide up the remaining region into thirds. We evaluate our function at those 2 points. We see the point on the left is greater than the point on the right. The function must be strictly decreasing to the left of the minimum. Therefore, the minimum cannot lie in the leftmost third. Okay, and here's the function we were finding the minimum of. Sure enough, the minimum lies in our remaining uncertainty region. With searching by thirds, we do 2 function evaluations in every iteration. We take the remaining section, we divide it into thirds, and then we evaluate the function twice. Evaluating a function could be expensive. It might mean conducting an experiment, or it might mean running some long computational process. It's a shame that searching by thirds requires 2 evaluations in every iteration. Furthermore, it is unable to take advantage of all the information that we gained from prior iterations. Golden section search solves this. So first, a note on the golden ratio. Its value is 1 plus the square root of 5 all over 2. Let's discuss some places where it is seen. First, we'll discuss the Fibonacci sequence. The Fibonacci sequence starts with 2 numbers, 0 and 1. Then what you do is you add up those 2 numbers together. In this case, 0 plus 1 is 1. Now you add up the last 2 numbers. In this case, 1 plus 1 is 2. Again, you add up the last 2 numbers, which yields 3, 5, 8, 13, 21. And this sequence goes on forever. Now you might think, what if I take the ratio of the current value to the previous value? And then I look at how that ratio changes as I go off to infinity. It turns out that value converges to the golden ratio. So that's one place it arises. Here's another. I'm going to make a rectangle, and the ratio of the width to the height of this rectangle is the golden ratio. Now I'm going to divide this rectangle so that the ratio of the height to the width of the smaller rectangle is the golden ratio. And now I'm going to divide that rectangle again, and again, and again, and again. This could go on endlessly. Now I'm going to create a spiral. The way I'm going to do that is by looking at the largest section of this partition and drawing a half circle. And then I'm going to do that for all remaining partitions. There's the spiral. Now it turns out that this spiral leads to an optimal packing. And we could prove this, or we could just ask nature. This spiral occurs naturally in many locations because it satisfies this optimal packing property. Here are a few more places where the spiral created with the golden ratio shows up. Okay, so this is a beautiful magic number. Let's see how golden section search uses this number. You have your interval A and B, and we're going to consider the length of that interval L. Now what I'm going to do is divide L by the golden ratio to create a new distance, and I'm going to create a candidate point at that distance away from A. I'm going to do the same thing with B. Here are 2 candidate points. We're going to evaluate the function at these 2 locations. We see that it's greater on the right than it is on the left. That lets us exclude this rightmost region. In our remaining candidate region, I'm going to call that length L. I'm going to divide L by D, and then I'm going to look at that distance away from A, and wouldn't you know it, that's exactly where our last candidate point was. I'm going to do the same thing from the right side of our remaining interval. That's our new candidate point. And now we only need to do 1 function evaluation. We see again that the point on the right is greater than the point on the left, so we could eliminate the rightmost region of our remaining interval, and that limits where the minimum is to this leftmost portion. We could do the same thing again, and here's the function we were minimizing. Here's the golden section search and code. It accepts inputs A less than B, which define our interval of interest, epsilon greater than 0, which will be our error tolerance, and we immediately set the golden ratio R. We set XL equal to A and XU equal to B. XL is meant to be X lower, XU is meant to be X upper, and D is equal to XU minus XL, all divided by R. We subtract D from XU to get X1. We add D to XL to get X2. These are our candidate points. We evaluate the function at X1 and X2 to get F1 and F2. And then we start the golden section search iterations. If F1 is less than F2, then the minimum lies in XL to X2. These instructions bring the upper point XU down to X2, create a new candidate point X1, and evaluate the function just at x1. There's only one function evaluation per iteration of golden search. If f of 1 is not less than f2, the minimum lies in x1 to xu. This brings the lower point xl up to x1, creates the new candidate point x2, and evaluates the function to find f2. Again, we return the middle point of our remaining uncertainty region. That concludes this lecture. Thank you for your attention.